Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to analyze a statically indeterminate torque-loaded shaft. So let's go ahead and look at the given information. Here we're being asked to determine the reactions at the fixed ends and draw the internal torque diagram. We're also being told that the torsional rigidity, which is the product of J and G, is constant. So in the figure, what we have here is a shaft that is fixed at both ends. Notice there's a fixed connection here at end A, and there's another fixed connection on the opposite side at end B. Now, throughout the length of the shaft, there are two applied torque moments. One is 400 Newton meters, and the other one is 500 Newton meters going in the opposite direction. And then we have some dimension lines here that tell us the locations of all of these critical points. So from point B to the 400 Newton meter torque moment, it's 0.25 meters, and then the distance between the two torque moments is 0.3 meters, and then the distance from the 500 Newton meter torque moment to point A is 0.35 meters, okay? So obviously this is statically indeterminate, and the reason is because we have two fixed connections and we only have one applicable equilibrium equation for torsion, okay? And so what I'm going to go ahead and do is I'm going to use this given figure also as a free body diagram of the entire system. And I'm going to go ahead and I'm going to draw a torque reaction here, which I'm going to call TA. And then on the opposite side, I'm going to draw a torque reaction here, which I'm going to call TB. And I drew them pointing in the same direction as each other, okay? Now remember, we're assuming the directions of these torque reactions, right? We assume a direction of a reaction, and if we do the calculations and one or both come out negative, that means that those reactions are actually pointing opposite of what we assumed. So this is what we have here. Now, as we get into the solution, the first thing I'm going to do is I'm going to write my equilibrium equation, okay? So what is my equilibrium equation going to look like? Well, for a torque-loaded shaft, it's the sum of the torques equals 0 along the length of the shaft. So what I do is I go from one end of the shaft to the other, and I just sum up all of those torques, and I be mindful of the directions of each one of them, right? Because some of them are in opposite directions relative to the others, okay? And so I need to have positive and negative signs reflecting that, all right? So if I put a little eyeball maybe out here, there's a viewpoint, and I look in this direction, okay? And I start with the torque reaction at A, all right? I can say counterclockwise is positive, and I can put my little eyeball here, okay? And so the first thing I see way back here is TA, and that's going to be going in a clockwise fashion, so that's going to be minus TA. And then in front of that, I see minus 500 Newton meters, and then in front of that, I see plus 400 Newton meters, and then at B, I see a minus TB equals 0, okay? And so we can either leave this like it is, or we can maybe consolidate and do a little bit of rearranging here. I can conveniently rearrange this if I want to as TA plus TB equals negative 100 Newton meters. All I did was I put the TA and the TB on the other side of the equation, and then which made them both positive, and then I said minus 500 plus 400 is negative 100 Newton meters. So this is going to be one equation, and that's our equilibrium equation. And as we see, we have two unknowns. So what's the second piece of information we need? Well, we need to set up our compatibility equation, right? That's going to be our second relationship. So I'm going to call this the compat equation. All right. Now the compatibility equation is going to relate angle of twist values to one another. Now, generically speaking, what we're going to have is the angle of twist at A relative to B should be 0. What does that mean? Well, that means that the angle of twist at this fixed connection relative to the angle of twist at the opposite fixed connection should be 0, because those two connections are fixed, right? They can't move. They can't twist or deform. So that's why we say those equal 0, right? Now, the question is, how do we expand this? Well, we're going to use method of sections to help us expand this out and build this relationship out more specifically, right? When I first wrote this down, I said, generically speaking, phi of A relative to B is 0, but I need it more specific for my particular problem here, okay? So what do I need to do? I need to build out what's happening there. So what I'm going to do is I'm going to say free body diagram number 1, okay? And I'm just going to start from one end of the shaft and go to the other end, the opposite end. It doesn't really matter which side I start with. So how about we just start with the TB side? That's where, you know, we're closer to our eyeball, okay? And so, again, we're using method of sections here, which we should be pretty comfortable with that at this point. So at the fixed end at B, what do we have? Well, we have that TB reaction here that we drew earlier. And then we have the shaft here, and we have that cut section there, okay? Now, how long is that? How long is this this segment right here? Well, we're going to be cutting just before we get to the 400 Newton meters. So we're going to look at the entire length of this, which is 0.25 meters, the entire length of this first segment, okay? So we can go ahead and make a little note here. This is 0.25 meters long, all right? And then what I'm going to do is I'm going to go ahead and draw an internal torque here. I'm going to call this T1, all right? And then I'm going to put a little eyeball here, and I'm going to look inside of that cut, all right? Now, when I look inside of that cut, what do I see? Well, I see a circular shaft, and I see T1, right? And what direction is T1 going to be going? It's going to look like this, okay? Again, think about what this eyeball is seeing as it looks inside of this shaft. It sees T1 curling around in this direction, but from this eyeball's perspective, that is clockwise, okay? And then behind T1, we see TB, that reaction, TB, that, again, we drew this reaction here, TB, from earlier. That's where it was earlier, okay? And so what do we do here? Well, we say sum of the torques equals 0, counterclockwise positive based on this little eyeball, and we're going to see that we've got TB minus T1 equals 0, so T1 just equals TB, okay? T1 just equals TB. And so what do we do next? Well, we go to our next free body diagram, okay? So let's say free body diagram number 2. And we make a cut inside of the second segment, okay? Make a cut inside the second segment. What's going to show up? Well, you know, TB is still there. This is still just method of sections right now. But now we have cut past the 400 Newton meters. We've cut just before the 500 Newton meters, okay? So we're cutting inside of this, but just before that 500 Newton meters. And so when we do that, what do we get? Well, first we need to probably draw that, that 400 Newton meters, okay? And then what dimension lines are here? This was 0.25 meters, and then the next dimension line was 0.3 meters. And when we open this up, what do we see here? Well, we see, you know, a T2 there, okay? We see a T2. And we look inside of that cut, and what do we see? Well, we see the shaft here, and we see a T2, and then behind that we see 400 Newton meters going in the same direction, and then behind that we see, of course, TB, okay? And then we're gonna say sum of the torques equals 0 based on that viewpoint. And so inside of this, we're gonna have TB minus 400 Newton meters minus T2 equals 0. And so we can get T2 as equaling TB minus 400 Newton meters. So there's T2, okay? And notice we're getting T1 and T2 in terms of TB, all right? And then finally, we can do a third one, free body diagram number 3. And here we're trying to capture that last segment, okay? And there's TB, and here's the 400 Newton meters, and then past that we have the 500 Newton meters. Again, we're following a very similar process that we've done the previous 2 times, just method of sections. 0.3 meters. This one's 0.35 meters from the original drawing. And then, of course, you know, we've got T3, and we've got the eyeball looking in, okay? And so what do we see? Well, we see the circular cross-section, and then we see a T3 here, and then behind that, we see 500 Newton meters going opposite of T3. Behind that, we see 400 Newton meters, and then behind that, we see TB. Oh, that should be dashed line, shouldn't it? Actually, all these should have been dashed lines, right? Because they're behind, so follow our proper graphics rules. And so what we do then is we're going to say sum of the torques equals 0, counterclockwise positive. There's my eyeball, and I'm going to have TB minus 400 Newton meters plus 500 Newton meters minus T3 equals 0. And so do a little bit of rearranging. We solve for T3, and we're going to get TB plus 100 Newton meters. So now what do we do? Well, we've got all these internal torques. We need to build them into the angles of twist, right? So what we're going to do is we're going to say Phi1, going back to the first free body diagram, is T1 L1 over JG, right? Now, what was T1 and what was L1? Well, T1 was just TB, and L1 is 0.25 meters. So we're going to say TB times 0.25 meters over JG, okay? What about Phi2? Phi2 is T2 L2 over JG, okay? Now, what's T2? Well, T2 is TB minus 400. So parentheses TB minus 400 Newton meters times 0.3 meters all over JG. And then Phi3 is T3 L3 over JG. And what is T3? Well, that's our TB plus 100 Newton meters times 0.35 meters over JG, okay? And so how do we relate these all together? Well, again, it goes back to the compatibility equation. So our compatibility equation says phi A relative to B equals 0. Well, what that means to us here is that when you add up these phi values, they should be 0. So we're going to say Phi1 plus Phi2 plus Phi3 equals 0, all right? And so then what we're going to do is add up these 3 expressions together, right? So we're going to say TB times 0.25 meters over jg plus TB minus 400 Newton meters times 0.3 meters over jg plus TB plus 100 Newton meters times 0.35 meters over jg equals 0, okay? Now, what do you notice here? You have a jg in all of these terms, and you have equals 0. So what you could do is, you could factor out jg and cancel it with the 0 on the right side of the equation. So then this starts to simplify down, right? You end up with let me color code this a little bit better. You end up with 0.25 TB, and then you end up with plus 0.3 TB minus, and I'm going to kind of multiply some stuff out here. So minus 120 Newton meters squared there. And then we're going to say plus 0.35 TB plus 35 Newton meter squared equals 0. And so what do you notice here? Well, we have one equation with the same one unknown in it that's showing up a few different times, and that's TB. So then what we can do is solve for TB here, okay? And so I'm just going to say 0.25 plus 0.3 plus 0.35 is 0.9 TB, and then I move some items to the other side of the equation, 120 minus 35, and I divide by that 0.9, and so I get 94.4 Newton meters as TB. Now that's part of my answer, right? Determine the torque reaction. So that's one of my answers. And now what I'm going to do is I'm going to substitute. So I'm going to say now substitute this into the equilibrium equation from earlier, right? And so what was our equilibrium equation way earlier? We scroll back up here and we had TA plus TB equals negative 100, right? So what I'm going to do is say TA plus 94.4 Newton meters equals negative 100 Newton meters. And I can get TA equals negative 194.4 Newton meters. Now that's the other part of my answer. So I have TB and I have TA as two parts of my answers. The next part is we're going to use these to draw the internal torque diagram. So to draw the internal torque diagram, to help me out, I'm going to go ahead and resketch what this shaft looks like now that I have the reactions, okay? And so TB is, of course, right here. That's the 94.4 Newton meters. Now, what about TA? Notice that we had a negative sign pop out for TA. What that means is that TA is pointing in the opposite direction of what we initially assumed in that first free body diagram. So notice that I'm orienting TA opposite of what I had originally drawn or had drawn at the beginning of this problem, okay? And then, of course, I've got my 400 Newton meters, and I've got my 500 Newton meters here. And then I've got some dimension lines. And if we recall, I believe this is 0.25 meters, 0.3 meters, and 0.35 meters. And so what I'm going to do is I'm going to say that, hey, this point right here, let's call this the origin, and let's call pointing towards A as the positive x-axis. So to draw that internal torque diagram, I'm going to put some axes here. I'm going to call this T Newton meters, okay? X in meters. And I'm going to put another viewpoint here. And just for direction purposes. And I'm going to say that going counterclockwise is positive based on that little viewpoint I just drew. And then I'm going to start sketching this out. So the first thing I encounter is the 94.4 Newton meters going clockwise, which means I'm going to jump down 94.4, right? And then nothing happens for the first 0.25 meters. So I'm going to stay constant for 0.25 meters. And then I'm going to encounter 400 Newton meters going clockwise based on this viewpoint, which is going to jump me upwards, right? So we say negative 94.4, right? This is really a negative here. And then we say plus 400. And so we're going to jump way up to a positive 305.6, okay? And then we stay constant for 0.3 meters, okay? So for this 0.3 meters, we're staying constant. And then we encounter this 500 Newton meters that's going clockwise based on this viewpoint. So I'm going to subtract that, and that's going to push me back down. That's going to push me down to a negative 194.4. And then we're going to stay constant for 0.35 meters. That's this 0.35 meters. And then we're going to jump back up 194.4 Newton meters because of this reaction here. So that's going to jump us up right here. And so this becomes the shape of our internal torque diagram. Now let's briefly make some comments about the directions here. Remember, the directions of all these torques are very dependent on where your viewpoints are, where those little eyeballs are. So if you define your eyeballs a little differently than what I did, you're going to get the same numerical values. You'll still get 94.4, you'll still get 194.4, and they're still going to be in the same physical directions as what we calculated, but you might have all of the values have the opposite sign, right? So what's positive in my video, in this video, might be negative on your paper and vice versa, depending on how you define your viewpoints. And even this torque diagram might be upside down if you define your viewpoints or your directions a little bit differently. So what's important is that you understand really clearly how you're defining your viewpoints and your directions, because that's going to influence the values coming out as positive or negative in a lot of cases. Now, so there are a few different right answers. It's just the values of being positive or negative might be different depending on what you call positive rotation or what you call where you're defining your viewpoints. So I just caution people on that. So that concludes this video. If you found this helpful, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.